Yes, very good. Thank you. Let me introduce the next speaker. Good morning. The next speaker is Hershel Farkas, and he will speak on Schottky Relation. Please.
Thank you very much. Let me begin by thanking the organizers, Krishna himself, for inviting me to this conference, celebrating Krishna's 60th birthday, especially since the subject matter of my talk is not exactly in the center of the ideas being discussed here. However, I will be talking about theta functions, or theta constants, which have been mentioned in several talks previously. Although the theta constants that I'll be talking about are higher dimensional ones, not the one-dimensional ones, which generally occur in the theories of partitions and Q-series and so on and so forth. However, I think that the result is sufficiently interesting, and perhaps I hope that some of you will find some interest in the topic. So, what is the problem I want to talk about? The title is the Schottky Relation. What are the Schottky relations? There is a space called the Zeekel upper half plane of degree G, denoted by sigma G, and that is the space of complex, symmetric matrices, positive definite, imaginary part. This is a space, obviously, of dimension G times G plus 1 over 2. On the other hand, if you're given a compact Riemann surface of genus G, and a canonical homology basis on this surface, that's a basis, let's call it alpha 1 to alpha G, beta 1 to beta G, satisfying the intersection properties given by this 2G by 2G matrix, then it's known that you can find a basis for the holomorphic differentials on this compact Riemann surface with the property that the integral, let's call it basis beta I over alpha j is equal to delta ij, the canonical delta. 1 I equals j, 0 otherwise. And when you integrate over the other set of G cycles, theta I over beta j, you get a matrix pi ij, and the point is that Riemann already showed that this matrix pi ij is a symmetric matrix and has positive definite imaginary part. So the Schottky problem is, you have the Zeekel upper half plane of degree G, you have this subset of the subspace of matrices which arise from compact Riemann surfaces together with a canonical homology basis, and you would like a description. You'd like to say, you'd like equations on the Zeekel upper half plane which cut out the set of these matrices, which we'll call the G functions, for reasons that those who know, and those who don't know, it doesn't matter. So that's the problem. Now, Schottky was the one who, I guess, I'm sure that Riemann thought of the problem himself, but Schottky was the one who stated this as a problem, and actually solved it in the case G equals 4, which is the first case that really arises. Because, as I said, the dimension of this space is G times G plus 1 over 2. The dimension of this space, at least for G greater than or equal to 2, is 3G minus 3. For G equals 1, it's one-dimensional. The difference between these two numbers vanishes when G is equal to 3 or G is equal to 2, and equal to 1 when G is equal to 4. So therefore, the first place this problem really arises as a serious problem is the case G equals 4. Now, Schottky, in fact, solved this problem when G equals 4, and he wrote down a relation that looked like this. where each of these Ri's is a product of 8 theta constants. Should I define theta constants, or is this, yes? Okay, let me just take a second to define theta constants. We have something called a G characteristic, epsilon epsilon prime, 2 by G vector, in Z to the G cross Z to the G. And then the theta function is defined in the following way. The theta function of characteristic epsilon epsilon prime, this is just a natural generalization of Jacobi's theta function. Of Z and tau is given by this ugly-looking series. You sum over all integer vectors in complex G space, exponential 2 pi I 1/2 n plus epsilon over 2 transpose tau n plus epsilon over 2 plus n plus epsilon over 2 transpose Z plus epsilon prime over 2. This is the theta function with characteristic epsilon epsilon prime. Z, of course, is in complex G space, and tau is a matrix in the Ziegler upper half plane. So if you let G equals 1, this is the usual definition of Jacobi's theta function. And we will be interested only in the value when Z equals 0, and those things we will call theta constants. And these theta constants have the following property. The reason I restrict Z to the G cross Z to the G, we can partition the set of theta constants into 2 sets, the even theta constants and the odd theta constants, excuse me, depending on whether the inner product of epsilon and epsilon prime is congruent to 0, 1, mod 2. It turns out when you have an odd characteristic, the function of Z which you get is an odd function of Z, and therefore that vanishes at the origin. So the theta constants, the odd theta constants are all 0. And generically, if it's an even characteristic, it doesn't vanish at 0. And those are the interesting theta constants to us. When I said before that Schottky wrote down his relation to genus 4 of this type, what I meant to say was that each Ri is a product of 8 even theta constants. So you have 24 theta constants taken out of the, I think, 136 even ones, and there's a relation between them, which he wrote down in a quite mysterious fashion. There is no complete solution to the Schottky problem for any G greater than 4 today. Although Ron Donaghy told me a few weeks ago that he thinks his student is writing a paper which will solve the case G equals 5. So this is it's an old problem. Now, almost 50 years ago, Harry Rausch and I made some progress on this problem. Actually, Rausch found a paper, an old paper of Schottky and Jung, where a statement is made. And the statement is roughly the following. There was something called the prim variety associated to a Jacobian variety, associated with a compact Riemann surface. This is a complex torus of dimension 1 less than the genus, so it's genus G minus 1. And it corresponds also to taking a smooth 2-sheeted cover of the original Riemann surface. Well, there are 2 to the 2G smooth covers that you can take, in some sense. And each one corresponds, if you like, to a point of order 2 in the Jacobi variety in the complex torus. If you want, you can think of these characteristics as representing points of order 2. And then, if you look at the point of order 2 corresponding to this characteristic, which is simple 1, the statement by Schottky and Jung, and I stress statement, so it appears that the following is true, that if you take the prim variety, which is what? The prim variety just is what? If you construct a 2-sheeted cover of a surface, a smooth 2-sheeted cover of a surface of genus G, you get a surface of genus 2G minus 1. And there's a homomorphism of that into the original surface, which has a kernel of dimension G minus 1. And the kernel, actually the component of the kernel containing the origin, is the prim variety. That's not important for our considerations. The point that Schottky would say is that if you look at the theta constants associated with the prim variety, and I denote them as being etas rather than thetas, just to separate the two, this is equal to k, which is independent of the characteristic over here, theta 0, 0, epsilon, epsilon, and theta 0, 1. And this we call the Schottky-Jung relations. Again, I stress, as far as I could tell, or Roush could tell, or anybody else, except there are people who seem to think that Schottky and Jung have proven that, but I don't know where. I think, provided the first proof of this, as almost 50 years ago, that Roush and I used this idea to write down equations which are satisfied by the Jacobians, by the Riemann surfaces which come from, by the period matrices, by the matrices which come from integration of holomorphic differentials on a Riemann surface. We were able to write down many equations which they satisfy. The problem was that we could not say anything about the functional independence of the relations we wrote down, even though we could write down lots and lots and lots. I'll show you in a few moments where these relations come from. That was one problem. The second problem was that we did not know whether there are possibly other components which weren't interesting, extra components, which so would be the Jacobians plus something else. But we were certain that some bright people would find the answer to that, and we expected that within 1 or 2 years the problem would be solved. Well, it's 50 years later, and as I said, the problem is still not solved, and I am not going to give you a complete solution to the problem today either. And let me explain at the outset why I'm not giving you a complete solution. I will write down equations which I can prove are functionally independent in a certain set. But the equations I'm going to write down are going to be equations of the same type that Schottky wrote down. No one raised their hand and said, but. What does that mean, the square root of Ri? Well, so I sort of preempted the question by writing plus or minus. So I didn't tell you which square root I was choosing. Well, in the equations I'm going to write down today, I also will have this plus and minus. I know that there is a choice of sign, which works, but I don't know which one it is. Now, actually, when I was discussing this with Peter Sarnak 2 weeks ago, and actually before, we had some correspondence on it, he says, this is a problem you give to a computer. Doron isn't here. If he was, I would give him the problem to give to Shalosh Be'echad, and he would know that solve it. But anyway, so this is a problem which still exists. So we don't have a complete solution to the problem. I can't say I'm writing down formulas because I don't know which choice of square root to make. And two, I still have no idea whether there are additional components or not. So how have I sort of made some advance by being able to write down at least things which are functionally independent? And the reason is another distinguished name in mathematics, Poincaré. See, Poincaré was interested in the same problem, but he was not as ambitious as Schottky, let's say. And what he said, I want to solve this problem. I want to know which are the Jacobians, but I'm only going to ask this question when I'm in a small neighborhood of diagonal matrices. You see, if you take a compact Riemann surface, you can degenerate it, and it becomes a product of fluoride. If it becomes a product of fluoride, well then the matrix which corresponds to it is a diagonal matrix. So just in a neighborhood, a small neighborhood of the diagonal, what are the equations which define the Jacobians? And he succeeded in solving this question for every genus. I'll just write down in genus 4, for example, he wrote down the equation I12, I34, I13, I24. Again, notice the square roots are going to appear. Again, plus or minus I12, I34, I14, I23. Plus or minus I13, I24, I14. And in genus 5, he writes down many equations. In genus 6, in every genus he writes down equations. And the point is that when you take the equation in genus 4, the one I've written down, and in genus 5, the same equation holds, but there are 2 additional ones that you can write down. In genus 6, you'll then get another 3 you can write down, and so on and so forth. In other words, these equations are, the genus 4 equation appears first, then the first 3 equations are the ones for genus 5, the next 6 equations are the ones for genus 6, and so on and so forth. Lovely. Okay. And it's easy to choose from Poincaré's relations. It's easy to choose a set which obviously are functionally independent, because after all, they're almost polynomial relations, except this ugly square root which appears here. I should have said, over here, when I said this is the name of the diagonal, what this means is that these pi ij's are small. They're close to 0. So small pi's, this is an asymptotic identity. Okay, so how can one perhaps use Poincaré to get Schottky? And the idea, actually, this idea was also due to Harry Rausch, who did it in genus 4. He wrote down a Schottky type relation. A Schottky type relation means an equation of this type, where you have the 24 theta constants appearing. However, when you looked close to the diagonal and you expanded this in power series around the diagonal, what you got was Poincaré's relation. So in other words, the title of his paper at that point was Schottky implies Poincaré. So that was lovely. Now, if you could do this in every genus, write down Schottky type relations, which near the diagonal are Poincaré's relations. Since the Poincaré relations, you know how to choose a functionally independent set. That would mean that the original equations which you wrote down would also be functionally independent. And that is what I have, in some sense, been able to do. So, no, there's no uniqueness. But there's also no unique expression over here. There are many different ways you can write down Schottky's relation. They're all equivalent, but there's absolutely no uniqueness. Okay, so this is the plan. Oh my God! Let me just tell you what we do. The main tool in this subject is something called the Riemann theta formula. Riemann's theta formula says the following: in any genus, if you choose characteristics delta delta prime, lambda lambda prime, mu mu prime, and then you have the following formula that is true. Here's the G. Theta delta delta plus lambda delta prime plus lambda theta delta plus mu delta prime plus mu prime theta delta plus lambda plus mu delta prime plus lambda prime plus mu prime is actually equal to the sum over all even characteristics of the same kind. Theta epsilon prime, theta epsilon plus lambda epsilon prime plus lambda prime, theta epsilon plus mu epsilon mu prime, theta epsilon plus lambda plus mu epsilon prime mu prime, and here I forgot to write the -1 to the lambda plus mu dot delta prime, and here I need a -1 to the lambda plus mu epsilon prime, and of course there's constant listed over here, -1 delta epsilon prime minus delta prime epsilon. This is a formula which is true all genus and due to Riemann. People ask me. Well, you see, what I decided to do is always choose my delta delta prime to be an odd characteristic. If I do that, this side vanishes, because you see then the value of an odd theta function at the origin. Now, I could have chosen any one of these could be odd. But in fact, in the application, what one does is chooses our delta delta primes so that they all, in fact, are odd. I can't explain that why. But that's what one does. Then you look at what you have on this side of the equation, and this gives you an identity. So for example, if we would take the case lambda lambda prime equal to 0, 1, mu mu prime equal to 0, 0, 0, 1, we would get a very, very nice equation. I'm not going to write it down because I see that time is already gone. We would get an identity. What Schottky did, develops a posteriori, is that he went one step further. Instead of only taking two guys like this, he decided to throw in a third guy. And then instead of having over here a product of 4 guys, he has a product of 8 guys. And since he wants a total degree to be 4 for some reason, which works apparently, you see these identities can be written if I choose the lambda and mu appropriately. This would be either a 4th power, square square, or a product of 4. So he said, I want a product of 8, but I want the degree to remain 4, so he threw in a square root. Okay, if I choose my lambda lambda prime and mu mu prime and nu nu prime to be the one that you would expect next, you can then show, you can write down this formula, and you can show that it holds on Jacobians. The reason it holds on Jacobians is that if you write out the expression, you see that you can employ the Schottky proportionalities, and the square root of a product of 8 then becomes the square root of a product of 4 squares. So they disappear, and you get an identity, which you have proven in the first case when you only chose these guys that those vanished, and therefore this vanished on Jacobians. And you get this lovely identity, which Schottky got. He didn't get it this way, but this is what you get. This is equivalent to his identity. So then the question then arises, so what's bad about that? Nothing. But the point is, you can't learn too much from that. The idea then is to convert this particular identity into one, which is still an identity, but also has the property that it reduces the Poincare into that. Now the tool for doing this is the transformation theory of theta group. You know that theta is a modular form for certain subgroups of the modular group. We can write down explicitly the formulas, and I can write down a symplectic 8x8 matrix, which actually will then act on this identity. Now each one of these theta constants to a different theta constant. There are constants as well. You have to cross it, you have to write out a common factor, cancel it to whatever these equal to 0, and you end up with a new identity. The new identity you end up with indeed does reduce to the Poincare relation near the diagonal. Now, I'm not going to do it because I'm out of time, but the point is, it's a lot of work. I mean, you have to compute and compute and compute. There's some shortcuts that you can take, but it's still a lot of work. Is this worth doing this work? And the answer is yes. Because if you succeed in showing this, I claim I have, then you don't have to make any further computations in higher genus. And the reason turns out to be you go to the following. In genus 4, I won't write it out, but the symplectic matrix looks like this, where the given D, C, D, and A, G by G. I should really call that M4. And MG would be D, C, B, A. Here I would have 0, 0, and here would be an I, G minus 4, the identity G minus 4 matrix. And here I would have 0, 0, 0, and 0, and 0, and 0, and 0, and 0, I, G minus 4. I would do the same thing in genus G that I did in genus 4. But if you look at the action of this guy, you see that its action on the first 4 columns of characteristics is exactly the action you had on genus 4, and everything else is the identity. So therefore, I no longer will have to make computations in genus, higher genus, and if you have a nice way of writing down the characteristics, which we do, the nice way of going from genus G to genus G plus 1 is by just looking 0, 0 over here, and these all the genus G guys. 1, 1 over here, the even guys. Here, the odd guys. Here, the even guys again. And here, the even guys again. These give you all the G plus 1 characteristics. And from these formulas, with the observation that everything is the same as genus 4 on the first 4 columns, you can write down these expressions. So therefore, what you see, and I'm going to show this now, but what you see is that you're going to get, again, this genus 4 Poincare relation, and you're going to get this in every genus. So how do you get the other relations? And that turns out to be embarrassingly simple. What you simply have to do is make permutations. And you can move these columns around any way you like, because moving columns around simply correspond to permutations on the rows of the symplectic matrix. And therefore, you can just by adjusting the columns, you can get any Poincare relation you want to get, and write down what the identity is. So therefore, as I said, we're able to write down these identities. We therefore, what is the conclusion of all this? The conclusion of all this, since we have functional independence near the diagonal, we're getting a variety which, of the proper dimension, which contains the Jacobians, which contains the space that we're looking for, and that's as much as we get. I don't know that if I move away from the diagonal, that these will remain functionally independent. In fact, they probably do not, because if it were true that they stayed functionally independent every place, then what would happen is I would have this space as a complete intersection, and I believe it is known that the space we're looking for is not a complete intersection. So something has to happen when you move it. But at least near the diagonal we have a finite set of equations which are functionally independent and which indeed vanish on the Jacobians, and I view that as being a significant advance, at least on what was known till now, because it seems to work in every genus. So I think that I won't bother you anymore, and hope that the ideas of these were semi-interesting to you. Thank you very much. I just should say one more thing, just basically about Krishna. I mean, Krishna and I have known each other for how many years now? Not as many as some other people here. I mean, I more or less came into the business a little bit because when I gave up on this problem, I decided if I look at genus 1, maybe I'll get some ideas there. And I worked for a while and got identities and partitions and Q series. It didn't help me with this problem, but okay. But that's when I met Krishna. And the fact that Krishna knows I'm no longer really doing that kind of stuff, and he still invited me to come, so I just attribute this to Krishna's interest, diverse interests in mathematics, and you should go on for 120 years. Thank you.
So I have one comment and one question.
Yes.
So the comment is that actually, because the functional equations are over the field of constants, so they are functionally independent globally. So whenever you have local functional independence, they also are functionally independent globally. There are no singularities in the algebraic relations. And this, yes, so that's the comment. The question is whether the relations of Schottky were for the zeta functions rather than for
No,
constants.
theta constant. I mean, you could write down relations to theta functions also, but apparently they're not necessary. Theta constants are apparently sufficient. But I didn't understand your first comment. Were you saying that they necessarily have to be functionally independent?
Yes, because that's over the field of constants. And therefore, whenever you have some local functional independence, it's global.
No, but I mean, functional independence simply means non-vanishing of the term.
The partial derivative.
Yeah. I mean, so just because it's not zero at a point, why can't it be zero at a point?
Because the relations over
Maybe these details should be straightened out later. And it could be that there's another question or a comment. it's not. Yeah, no? Is there?
Good.
Well, I have a question.
Yes.
What are Riemann's relations? You wrote on the board.
What are these relations?
There should be an equality there.
Isn't there?
That's right. Yes, that's right.
Oh, there was,
I
yes,
see.
there was an
There
equal.
was
And then I had to move it over a bit to put in the constant. I neglected to write. That's what happens when you get older.
Yes, I know this. Aside from that, there was this other approach to the Schottky Relation on the phase trisecant relations and solution of the KP equation. You want to comment on how that relates to this?
Well, it doesn't, I can say that it doesn't relate to this at all. My dream was to find a connection between KP, Arnold's work, and this kind of stuff. And I search and I search and I search. I found no common ground. What I can say is that the point of view using the KP equation, it also gives a solution. Correct. However, if you ask anyone, given a matrix, is this broken or not, they'll say, are you kidding? While if you use this method, you can check whether it's small, because these series converge very, very rapidly. So you can tell whether something's zero, or you can certainly tell when it's not zero. So there is an advantage in this method.
Okay, I think I have to conclude the session, and so let's thank the speakers.